This is another fundamental area. This is an fundamental additive manufacturing process. We have two versions. The first one is material jetting, and the second one is binder jetting. In the material jetting case, we are jetting the materials on the beds at very high speeds. And in the binder one, we have again a powder bed, but this time we are jetting the binders on the bed. Now we will see the fundamentals, their details, and they in common. We can say that jetting the powders, jetting the material powders or binder powders on the powder beds. And sometimes they are also called as printing processes. Now I will start with an example here. Can anyone tell me the main advantage if you look at just this picture? The advantage of jetting processes.
Color.
Yep, as you see, we have colorful parts and assembled parts. As in the case of powder bed fusion processes, we can have assemblies. You don't need to do them after the parts are fabricated. Another issue is that if you use colorful binding agents, we can have such colorful parts. And Hussein has a question. So what happens if you have powders inside the parts? We don't have such cases, Hussein. It's not possible in powder bed fusion processes. You can always produce solid parts. We don't have infill percentages in the powder bed fusion CAM software. It's only possible with FFF. So now let's start with this video. Let me arrange it. Hope we don't have any ads. Okay, we don't have. Let's switch to theater mode and share the video with you. So this is an Object 500 system.
We're always striving to enhance the design process. We're always asking ourselves, how can we help designers convey their ideas, their creativity? It's our passion to empower designers with true design freedom, to help the most astounding ideas move forward. Conics multi-material 3D.
You can see even they can have translucent materials, transparent materials, colorful materials, assembled structures. This is all possible with such jetting processes. And this one is called as Object. The statistics company is popular for their fused deposition modeling, but they're also working with object or jetting technology.
Technology from Stratasys is our expression of this passion. Now, we've created a new 3D printer, the Object 500 Conics 3, and we've radically enhanced the foundational elements of Conics technology to give designers more choice, more expression than ever before.
Conics technology has always worked by combining two model materials inside a 3D printer to create a variety of composite materials in one print job.
So as he said, they can produce composite parts having different materials. You see, one translucent material, one other colored material.
In one print job. With Object 500 Conics 3, we've expanded the technology.
So now you can see the fundamentals a little bit. We have a kind of a head. This head is actually scanning the plane from left to right or right to left. While it's going, as you can see some light, right? So which means that they are jetting some kind of photopolymer. And while they are jetting it, they also do polymerization with the help of this UV light. But these things happen just less than a second. This polymerization happens very fast way.
To let you start with 3 model materials, and for the first time ever with PolyJet technology, you have the ability to 3D print in color.
Colors with Conics 3 are vibrant and beautiful. You can pick from 10 color palettes for accurate and repeatable color with every build. You can mix colors with clear. You can mix colors with rubber-like. You can put 3 base colors into the Conics and build one model with 45 different colors. You can print digital ABS in the same model with rubber-like components. And you can do all this with PolyJet Technology's signature smooth surfaces for astonishing fine detail. Designers in the consumer goods industry, who are always improving on their last design, can integrate their innovations more easily than ever before and stay ahead of consumer trends. For important design reviews, Connex 3 will help you make beautiful prototypes quickly. You'll get accurate testing and thorough feedback before you go into production. You'll gain confidence with your ideas and wow your clients and focus groups with brilliantly colored concept models. You can increase your prototyping throughput by building models with a wider variety of materials and colors on the same tray. These new capabilities change everything. With the ability to print with 3 base materials, your creative possibilities increase exponentially. The ODTÜ 500 Connex 3 challenges your idea of what 3D printing can do and what it looks like. We can't wait to see what designers do with it.
With the Connex 3, we can better duplicate the material properties.
So I think that's enough for this company. Let's switch to our slides. So let's start the discussion of these jetting processes, material binder jetting. But their fundamentals are very similar to the inkjet printing, the things we are using in our daily printing of sheets. In that ones, we were jetting inks, but right now we will be jetting materials, some actual material or binding materials, but the fundamentals are the same. So we need to have a kind of a hat, and that hat should be responsible for jetting materials. And now this print, I think the initial printing technology is used in, obviously, in different fields, in additive manufacturing, optics, and even electronics can be packaged with the help of these printing technologies. But now we will be focusing on a different technology in 3D printing. We will discuss some achievements, some research and industry and academia. So let's start from the basic things, some history. It started actually around 1980s. They had the first type of jetting process called as ballistic particle manufacturing. The fundamental idea was similar. They were jetting very small particles at high speeds and try to manufacture some parts, difficult to manufacture with conventional approaches. And then they had very similar ones like model maker. I don't want to show them right now, but please make sure that you watch all these in your free time. The model maker is one of the first and commercialized the jetting process. And then we have another one, Actua Thermojet, from a different company, 3D Systems. And now we have Stratasys, the one actually we watched a moment ago. They also focused on jetting processes. Since it's a quite advantageous and they're not using laser, so it's an expensive machine in terms of the hat. But once they add different feature, they increase the cost of the machine. But I can say at least in terms of the hat that they're not using laser or powerful equipment at the hat side. The hat part of is cost efficient, I can say. And all of these actually commercial products were based on waxy thermoplastics. They were not using photopolymers. They were using thermoplastic like ABS, PLA, or some other types like in the form of wax. And we were mainly using these type of materials for investment casting and concept modeling. But the one we watched a moment ago is not using such waxy material. They are using photopolymers. On the other hand, on the binder side, actually, this was patented by MIT around 1990s. But these days, obviously, the patent has expired. And even in Turkey, we have some companies working on binder jetting processes. And the fundamental thing is that it's very similar to selective laser sintering. Instead of actually using a laser, they are jetting binding agents. But the rest is the same. We have powder bed. Powder is somehow spread on the table, and then these binding droplets are deposited on the bed. With the help of them, the powders are joined together, and this is repeated for upcoming layers. And we have some companies using this fundamental approach. And now I will show you a website, a very old website, but this is how MIT approached this patent. They license it to different companies. As you see, they have right now 6 companies are using this patent. They name their technology as 3-dimensional printing. So that's why sometimes you will see these letters, 3DP, as instead of binder jetting. Some people prefer to use 3-dimensional printing or simply 3DP, but they're all referring to the same technology. And we'll have a look at some of these companies, and MIT licensed this patent in terms of materials. For instance, one company is just working with metals, the other one is working with just polymers, and the other one is working with only ceramics. Let's have a look at the main technology here, the binder jetting technology. As I mentioned, the fundamentals are very similar to selective laser sintering. So we are spreading the powder on the table and then jetting these binding agents. And with the help of these binding agents, the powders are joined and we will have a green compact product. This is the finished product, but the process is not finished. We need to again do some sintering operation, and maybe even we need to do some infiltration. And we have some other things, applications. As you see, in the earlier days, these are very primitive pictures. They use it for composite printing, for metal printing, for ceramics printing. But right now, as I said, the patent is expired, so anyone can work on this technology. So these days, as I mentioned while discussing the objects, while watching the strategist video, people are preferring to use photopolymers, and they mostly use acrylate type of photopolymers. And for instance, in the object 500, we even have more than 1,000 of nozzles. So while it's passing from left to right, with the help of these nozzles, it can distribute or deposit this many drops at a time. So which companies are leading this technology? We have Solidescape. They only use 2 jets at the same time, so we can say that their approach is a kind of a point-wise, and they are using thermoplastic materials in a waxy, let's say, form. We have 3D Systems working on a technology, and they have many nozzles, hundreds of nozzles, but the biggest company is actually Stratasys, and their models are called as Object, and they make use of line-wise approach. They have many nozzles, and while they are jetting these binding agents, they do the curing right on the deposition. They have lights, as we have seen on the video, around the nozzle. Once the actually photopolymer is jetted through the nozzles, they are cured while they are in air or when they just hit the bed. So this is the main difference with respect to the previous ones. And for the support structures, they use a different material. It's a very gel-like material. It's quite easier to remove after the part is finished, and we can do the removing operation by using, again, a kind of water jet. This is a close-up view of the hat. This is a jetting hat. As you see, we have thousands of nozzles, and they have UV light right here. So once they jet this binding agent on the bed, the agent is cured with the help of the light. And you can see we have some different colors here. Some part is support structure and some part is model material. And you can remove this support structure by your hand or with a kind of a water jetting system. So we have, as I mentioned, we have different companies using these technologies, and they have different sizes. For instance, Object 1000 have a very large build volume, and it's especially useful for medium-sized production. And you can see that their layer thicknesses are quite good, around 16 micrometers, which is not obtainable in FDM, FFF, or SLA. They have high, very low resolutions. But as you see, their overall cost is too much. Around $1 million, not equal to 1 million, but about $500,000, you can obtain this quite large object system. Since they are the only company, that's why they are keeping the prices very high, even though they do not use laser, very, let's say, costly products. The overall system is quite expensive. So what are the advantages of these jetting processes? Since for the primitive ones, we can say that they have low cost. They do not use lasers. They are using standard components like XY motions or Z motions. The rest is the same. Another thing, since they don't have any laser, or they make use of thousands of nozzles at the same time, it's quite high speed. With a single pass off the table, you can, let's say, join the powders in just a few seconds. And you can do it in a very small scale or large scale. So we can say that it's scalable, can make use of multiple materials, even the colored ones. And we have such companies working on colored jetting process like Z Corp or Surfaces. On the other hand, we also have some disadvantages like limited materials. They can mostly use waxy thermoplastics or photopolymers. For the material jetting, on the binder jetting side, they can use metals and some ceramic type of materials. And for the general ones, just we have companies having higher accuracies than SLA, but most of the materials jetting and the binder jetting process have less accuracies than SLA process, but they are actually, I can say that for the larger products, for very large, let's say some meters of products, the accuracies are a bit less than FFF systems, but their accuracies are a bit higher for desktop type of FFF system. So we cannot easily say that one has a better accuracy than the other one. We should check their properties, check their build volumes and slicing thicknesses. Any questions, guys, on these fundamentals about material jetting and binder jetting processes? I didn't discuss much on the material jetting, but in the material jetting side, the nozzles are responsible for jetting the original material. If you watch the videos, actually I post their links on the initial slides, you will see that there are such material jetting process. But these days, the most popular one is actually the binder jetting process. Since it's much easier to do, you spread the original material powder and then you simply jet the binding agents. That's why I focus more on the binder jetting side. Bartu, I think you have a question.
Evet hocam, şeyi soracaktım da küçük parçalarda jetting'in daha accurate olduğunu söylerken daha büyüyünce ne değişiyor da accuracy düşüyor, onu ben pek anlayamadım da.
If the size, the build volume is larger, then that means you need to position your head properly. You cannot use a very large head passing just once and jetting all these agents on a layer. It needs to actually do it, let's say, in a kind of a zigzag way, and that will decrease the accuracy. But if the table is small, then with a single pass, it can cover the whole table. But if the table is, let's say, a large one, it needs to pass it maybe at least 2 times or 3 times. But if the table is a very small one, it can pass it with a single movement. That's why it will affect the accuracy, and you need to control it in a proper way. So many things will be in your, let's say, table, and You need to control all of these at the same time, and they will in result decrease the accuracy of jetting, especially for the larger parts. Any
Hocam
questions, guys? Yep.
ben de bir şey sorabilir miyim? Direct printing'de bed yok mu? O izlettiğiniz videoda sanki kask üretiminde bir herhangi bir yatak tarzı bir şey yoktu direkt. FFF gibi sanki yukarı doğru çıkıyordu layer'lar.
No, the part is actually going down, but the thing is that they can use the part of a bed. They cover, let me go back to the previous slides. Assume that this is their whole plate, but they do not use, sometimes depending on the size of the shape, they do not need to use the whole, let's say, I can say the whole region. Depending on the size of your scanning hat or the jetting hat, if your part is inside this one, let's say, width of your jetting hat, then you may just do the process on this line. But if your size increases, then you may need to have another pass of your jetting hat. That in that case, you need to cover the whole, let's say, powder bed. But this one, this binder jetting system, actually, as you pointed out, thank you for that, they do not need to have a complete powder bed. With the help of this supporting agent, they cover the boundaries of the original material. Assume that this is the original part we want to print, this region. And the remaining of this volume is covered with the supporting material. But as I said, they're not covering, the support material is not covering the whole build volume. This can be considered as an advantage.